Right now, your phone is correcting for time running at 2 different speeds. No, seriously. High up in orbit, the clocks on GPS satellites are ticking just a little bit faster than the clock on your wall, about 38 microseconds faster every single day. If your phone ignored that tiny difference, that time warp predicted by Einstein a century ago, your GPS location would drift by more than 10 kilometers. Every single day. You would be lost in your own city, thanks to a few lines of math. Which raises an absolutely terrifying question. If math is just something we invented, a useful game with numbers and symbols, why does the universe, from the flow of time itself to the spin of a distant galaxy, seem to be following the rulebook? Is reality written in a secret code we're only now starting to decipher? Today, we're auditing the source code of the universe. We're going to test the radical idea that mathematics isn't just a tool, it's a form of cosmic compression. It's the universe's most elegant zip file, the shortest possible description for why anything stays the same in a world of constant change. We're going to ask a simple question. Is the universe rewarding us for finding the symphony hidden under the static? Let's start with our first piece of evidence. And it's a big one. Symmetry isn't just about looking pretty. It's the law. In physics, symmetry isn't a decoration. It's not about a nice pattern on your wallpaper. A symmetry is any transformation that leaves the rules of the game unchanged. Think about a perfect snowflake. You can rotate it by 60 degrees, and it looks exactly the same. The rotation changed the snowflake, but its appearance, the thing we care about, is invariant. For centuries, scientists saw these symmetries everywhere, but they seemed like happy accidents. That is, until the early 1900s, when a brilliant mathematician named Emmy Noether stepped onto the scene. In a world dominated by men, she forged one of the most profound and beautiful theorems in all of physics, and it's a master bridge connecting what looks the same to what is the same. Noether's theorem is staggering. It says, for every continuous symmetry you find in the laws of physics, there must be a corresponding quantity that is conserved. It's not a coincidence. It's a guarantee. Let's break that down. Do the laws of physics care if you run an experiment today, or tomorrow? No. The formula for gravity doesn't have a calendar. Because of that symmetry, that indifference to the shifting of time, energy must be conserved. The universe balances its energy checkbook perfectly, all because the rules don't change from Monday to Tuesday. What about moving your experiment from New York to Tokyo? Do the laws of physics change? No again. The universe has no favorite spot. Because of that symmetry in space, momentum must be conserved. That's why a rocket can coast through the vacuum of space without its engine on. There's nothing to stop it, because no point in space is any different from the last. And what if you just turn your whole lab around to face a different direction? Do the laws suddenly change? Of course not. Because of that rotational symmetry, angular momentum is conserved. That's why a spinning ice skater can pull in her arms to spin faster. The universe insists that her total spin stays the same. This is our first massive clue. Symmetries, these ideas of what stays the same when you shift or turn, aren't just concepts. They are physical laws. Noether gave us the decoder ring. Math works, at least in part, because it's the language of symmetry. It's the language of invariance. Okay, that's wild. The universe has to follow the rules of symmetry. But what happens when the math predicts something no one has ever seen before? What happens when a scribble on a piece of paper can steer a spacecraft, or find a ghost planet? This is audit point 2. Our equations have an almost supernatural ability to see into the dark. Let's travel back to the 1840s. Astronomers are baffled. The planet Uranus is misbehaving. It's wobbling in its orbit, deviating from the path Newton's elegant law of gravity says it should follow. Something is pulling on it. But what? Most astronomers grab their telescopes, scanning the dark, hoping to catch a glimpse of the culprit. But a French mathematician named Urbain Le Verrier grabs his pen. He doesn't look at the sky. He looks at his equations. For months, he performs fantastically complex calculations, using Newton's laws to work backward. He asks, if Uranus is being pulled, where must the thing pulling it be? His math tells him. He scribbles down a set of coordinates, a precise location in the night sky, and sends it to the Berlin Observatory. The letter arrives on September 23, 1846. That very night, astronomer Johann Galle points his telescope exactly where the math told him to look. And within 1 hour he finds it. A new planet. Neptune. A planet discovered not with glass and light, but with ink and paper. Let that sink in. A human mind, using an invented symbolic language, reached across billions of kilometers of empty space and pointed to a world no one knew existed. And this is not a one-off. Just a few decades later, James Clerk Maxwell unified the laws of electricity and magnetism into 4 famously beautiful equations. But these equations contained a surprise. They predicted that waves of electromagnetism should travel through space, at the speed of light. He had, on paper, predicted the existence of radio waves. It was decades before Heinrich Hertz actually generated and detected them, proving that this mathematical ghost was real. A voice carried on nothing, leaping across oceans. All because the symbols said it had to be so. And it just keeps going. Einstein's curves on paper become the GPS corrections we just talked about. Schrödinger's bizarre wave equation for quantum mechanics gives us the precise colors of light emitted by atoms, and forms the bedrock of every semiconductor in every computer and phone on Earth. These are not small wins. This is math telling us about the fundamental structure of reality before we have the tools to see it ourselves. This is where it starts to feel less like we're inventing a tool, and more like we're finding a map. Which leads us to our third audit point. How does math achieve this incredible power? The secret is compression. Think about a zip file. You can take a 1,000-page novel, run it through a compression algorithm, and squash it down to a tiny file you can email in a second. Critically, you haven't lost a single word. The information is all there, just encoded in a much, much more efficient way. Mathematics is the ultimate compression algorithm for reality. Take something messy. A sound wave from a song, the jagged signal of a heartbeat, the complex color profile of a sunset. A French mathematician named Jean-Baptiste Fourier discovered you can break down any messy signal, no matter how chaotic, into a simple recipe of perfect, repeating circles, sine waves. It's like a master chef tasting a complex stew and instantly telling you every single ingredient, and its exact amount. A song becomes a list of frequencies. A heartbeat becomes a stack of pure rhythms. That's Fourier analysis. And it's not a trick, it's a deep truth about the world. It's why we can compress music, sharpen blurry images, and even see inside your brain with an MRI. We are decompressing reality's code. Or think about calculus. It's the magnifying glass for change. It takes the terrifying, continuous flow of motion and reframes it as a series of simple steps, the change in position, and then the change in that change. It allows us to calculate the arc of a baseball, or the orbit of a planet by compressing an infinite number of moments into one elegant equation. But the most profound compression of all might be something called the Lagrangian. It sounds complicated, but the idea is breathtakingly simple. You can describe the entire future behavior of a physical system, a pendulum, a planet, a roller coaster, with a single, compact mathematical sentence. That sentence describes one simple rule: nature is lazy. It always chooses the path of least action. Imagine a traveler trying to get from one point to another. Of all the infinite possible routes, they will always choose the one that finds the most perfect, efficient balance between time, energy, and the constraints of the road. That is what a Lagrangian captures. It's the shortest possible story for why a system does what it does. And it works. From a modern algorithmic perspective, the best theories, the ones we keep, are the shortest programs that have the widest reach. The minimal recipe that reliably bakes the most different kinds of cake. The goal of science is to find the ultimate zip file for the universe. And it turns out, we may be biologically programmed to do exactly this. Our brains didn't evolve to do quantum mechanics, they evolved to survive. We notice the repeating pattern of the seasons because that tells us when to plant. We spot the symmetry of a predator's face hiding in the bushes because that warns us in time. We are pattern-matching survival machines. The math we keep is the math that compresses reality best. We are nature's archivists, obsessed with finding what persists. But let's stress test this beautiful idea. Because this seems too neat, too perfect. If math is just a compression of reality's patterns, why does it sometimes feel so weird? Physicist Eugene Wigner called it the unreasonable effectiveness of mathematics. He was mystified by how often a piece of math, invented by mathematicians just for fun, with absolutely no practical goal in mind, would turn out decades later to be the precise, indispensable language needed to describe a new discovery in physics. The most famous example? Imaginary numbers. The square root of -1, labeled I. For centuries, it was a mathematical curiosity, a toy for a geometer's playground. It was literally called imaginary. It couldn't possibly correspond to anything in the real world. Until the birth of quantum mechanics. Suddenly, physicists discovered that this imaginary number was not just useful, but essential. It's baked into the very heart of Schrödinger's equation. The real world, at its most fundamental level, runs on imaginary numbers. How can that be? Why would a playground curiosity be the native language of reality? And then there are the edges where our elegant compression seems to fail completely. Where the code of the universe becomes a tangled mess we can't seem to zip. Think of the smoke curling from a candle, or the water crashing over a waterfall. That's turbulence, the wild handwriting of fluids. We have the equations for it, the Navier-Stokes equations, but we can't find tidy solutions. It's so hard, in fact, there's a $1 million prize waiting for anyone who can prove whether smooth, predictable solutions even always exist, or if they sometimes just break apart into mathematical chaos. Think about biology. A simple string of amino acids, a protein, snaps itself into a hypercomplex, precise 3D key in a fraction of a second inside a cell. But the number of possible ways it could fold is astronomically huge. If it tried every option, it would take longer than the age of the universe. Yet life solves it instantly. Our math can't keep up. And then there's chaos theory. The idea that tiny, imperceptible differences at the start can snowball into wildly different outcomes. The famous butterfly effect. It's like whispering into a microphone and having an entire arena roar back at you. It sets a fundamental limit on our ability to predict the future. Worst of all, in the 1930s, a logician named Kurt Gödel came along and proved something devastating. He showed that in any mathematical system rich enough to do basic arithmetic, there will always be true statements that you cannot prove to be true within that system. It's as if every map, no matter how detailed, must contain a white patch that says here be dragons, a territory it can describe but never, ever fully chart. A ceiling is built into the logic itself. So what do we do with this? We have a system that is unreasonably effective on one hand, and frustratingly limited on the other. This brings us to the deepest, most profound audit point of all: what even is math? Is it out there, waiting to be found, or is it all in our heads? The philosophers have been fighting about this for centuries. One camp is the Platonists. They argue that mathematical objects, numbers, circles, theorems, are real. They exist in some timeless, abstract realm, and we don't invent them, we discover them, like explorers finding new continents of pure logic. A circle was a circle long before any human drew one. Another camp, the nominalists, says that's nonsense. Math is a fantastically useful story we tell ourselves. A beautiful, powerful human invention, an instrument we've tuned to describe nature, but it's not nature itself. The symbols are just symbols. There's a middle path called structural realism. It says what's real aren't the things themselves, but the relationships between them. The pattern of connections. Maybe it doesn't matter if a number 2 exists, what's real is the relationship of doubleness. And then there's the most radical idea of all, from physicist Max Tegmark. His mathematical universe hypothesis. He claims it's not that math describes the universe. He says the universe is a mathematical structure. Full stop. Reality is math. In the same way that a symphony isn't described by its notes and intervals, it is its notes and intervals. We're not living in a world explained by math. We are living inside the equation itself. It's a mind-bending claim. And it leads to a strange thought experiment. Maybe we're just biased. Maybe we only find math so effective because we live in a pocket of the universe where stable patterns can exist. In regions with no laws, no symmetries, no repeating structures, life and intelligence could never emerge to notice them in the first place. Consciousness might be a byproduct of compressibility. We are fish who just discovered water, marveling at how perfectly suited it is for swimming. So let's perform one final stress test. Imagine a universe with zero symmetry. Every single moment is totally unique. Every place is utterly singular. Every rotation creates something new. There's no reliable sunrise. No repeating rhythm. Nothing is conserved. Could an intelligent mind evolve there? Without repetition, there can be no memory. Without invariance, there can be no laws to learn. Without patterns, prediction is impossible. What language could possibly exist when nothing could be named twice? It's hard to imagine anything but a universe of pure, unthinking chaos. So, what's the verdict? Where does our audit leave us? The evidence points to a stunning, interlocking conclusion. A middle path. Math is an interface. A co-creation between us and the cosmos. The universe genuinely possesses deep, real patterns and symmetries, invariances. And our minds, being pattern seekers, have invented a symbolic language, a set of handles to grab onto them. The discovery of the lock and the invention of the key happen together. And this changes what it means for something to be real. If the invariances are what's fundamental, then objects are secondary. A thing, like an electron or a planet or even you, is just a knot in the flow, a collection of patterns that stays recognizably the same when we shift our perspective, wait a moment, or turn our heads. Reality isn't the stuff. Reality is the persistence of patterns. This gives us a practical compass for the future. To understand more about anything, from physics to biology to our own behavior, we have to hunt for symmetries and find better ways to compress them. We have to ask, what stays the same when everything else changes? Where those patterns hold, we can predict. And where they break, that's where the real excitement is. That's where we'll find new laws, new phases of matter, new stories that demand a new kind of math. The next great revolution in physics will almost certainly come from discovering a new, deeper symmetry, a new invariance that finally compresses gravity and quantum mechanics into a single, elegant piece of code. So, we began with a simple line on a piece of paper, a doctor reading a heartbeat, and a satellite guiding you home. And we found that the strange power of mathematics comes from its ability to capture the soul of reality, the part that doesn't change as the world turns. From the universe's perfectly balanced checkbook guaranteed by Noether, to the hard limits of knowledge drawn by Gödel, the story is the same. Math is the shadow reality casts when we shine the light of invariance upon it. So tonight, try a little audit of your own day. What was the invariance? What pattern persisted from your morning coffee to your evening commute? If you had to write a single-sentence Lagrangian for your choices today, the rule that predicted the path you would take, what would it say? What is the irreducible, compressed truth of your day? So we've audited reality's source code, but what about the clock it runs on? On the end screen, you'll find our next audit where we ask, is time even real, or is it the most stubborn illusion our minds have ever created? Before you click, I have one question for you. What's one piece of math you use every single day, even if you don't think about it? For me, it's the simple ratios in cooking. Let me know yours in the comments below. And if you're the kind of person who questions everything, who wants to see the code behind reality, then you're in the right place. Hit subscribe and join our daily audit of the universe.